A forest fire has been burning for several days. The burned area in acres is given by the equation y equals 4,800 times 2 to the power of d, where d is the number of days since the area of the fire was first measured. Number 1, complete the table. So as we complete the table, if we say that d is 0, then 4,800 times 2 to the power of 0. Anything to the power of 0 is 1. So that's 4,800 times 1, which equals 4,800. And we also know that because in an exponential function, the number that is by itself is our y-intercept. This is our starting amount. So now we can go to the next box. If we have 4,800 times 2 to the power of negative 1, a negative exponent means 1 over. So that becomes 4,800 times 1/2, or 1 over 2 to the power of 1. And 4,800 times 1/2 is 2,400. Now if we go to the next one, 4,800 times 2 to the power of negative 2, that becomes 4,800 times, remember the negative exponent means 1 over, that's 1 over 2 squared. 1 over 2 squared is 1/4, and 4,800 times 1/4 is 1,200. Next, 4,800 times 2 to the negative 3 means 4,800 times 1 over 2 cubed, which means 4,800 times 1 over 8, which would then be 600. And our last box in the table, 4,800 times 2 to the negative 5 is 4,800 times 1 over 2 to the power of 5, which is 4,800 times 1 over 32, which would be 150. Number 2, look at the value of y equals 4,800 times 2 to the power of d when d equals negative 1. What does it tell you about the area burned in the fire? So for number 2, when d equals negative 1, it tells us 2,400 acres had been burned 1 day before measurements had been taken. What about when d equals -3? Well, when d equals -3, there had been 600 acres burned. So, when d equals -3, 600 acres were burned 3 days before measurements were taken. Because remember, day 0 is the day that they took a measurement, so negative days would be days before measurements had been taken. And number 3, how much area had the fire burned a week before it measured 4,800 acres? So that would tell us 4,800 times 2 to the power of -7, because a week is 7 days. So if we want a week before, then we want -7 to be our number of days. This becomes 4,800 times 1 over 2 to the power of 7. And if 2 to the power of 5 was 32, double that again, it becomes 64. Double it again, that becomes 128. So that becomes 4,800 times 1 over 128. So if I said 4,800 divided by 128, we get 37.5. So that means 37.5 acres were burned a week before measurements were taken. If you have any questions about how I answered this practice problem, please use this time right now to ask for clarification. The value of a home in 2015 was $400,000. Its value has been doubling each decade. If V is the value of the home in dollars, write an equation for V in terms of D, the number of decades since 2015. So what they want us to do is write the function notation equation that represents this situation. So they're telling us to call it V for value, using D, the number of decades since 2015, and that is going to equal the starting value in 2015, 400,000, times our factor. If it is doubling, the factor is 2, and our input is the exponent D, which stands for decades. Number 2, what is V when D equals -1? So we can say V of -1 equals 400,000 times 2 to the -1, which equals 400,000 times 1 over 2. And 400,000 times 1/2 is $200,000. What does this value mean? It means the home was worth $200,000 one decade before 2015, or in 2005, because a decade is 10 years, so 10 years before 2015 would be 2005. The value of the home was $200,000. Number 3, what is V when D equals -3? What does this value mean? So now V of -3 equals 400,000 times 2 to the power of -3. 2 to the power of -3 equals 1 over 8, because 2 cubed is 8, and negative means 1 over. And 40,000 times 1/8 is $50,000. And if we're saying decades is -3, then that is 3 decades before 2015. A decade is 3 years, so a decade is 10 years, so 3 decades is 30 years, and 30 years before 2015 would be 1985. So that means in 1985, The value of the home was $50,000. If you have any questions about how I solved this practice problem, please use this time right now to ask for clarification. A fish population P can be represented by the equation P equals 800 times 1/2 to the power of T, where T is time in years since the beginning of 2015. What was the fish population at the beginning of 2012? So P of -3, because if we are representing T as the time in years since 2015, and we want the population in 2012, that's 3 years earlier, so we would say -3 is our years. That's going to equal 800 times 1/2 to the power of -3. The negative means 1 over. If I have 1 over 1/2, then dividing by a fraction is the same as multiplying by its reciprocal. So this 1/2 becomes 2 to the power of 3. 2 cubed, or 2 to the power of 3. 2 times 2 is 4. 4 times 2 is 8. And 800 times 8. 8 times 8 is 64 with 2 zeros. So the answer would be D, 6,400. So this means the fish population is declining, which is what we would expect if our factor is a fraction less than 1. So 3 years earlier, the population was 6,400. It halved in 2013 to 3,200. It halved in 2014 to 1,600. And then it halved again in 2015 to be 800, which is what our initial population is, measured in 2015. If you have any questions about how I solved this practice problem, please use this time right now to ask for clarification. The area A of a forest in acres is modeled by the equation A equals 5,000 times 5/4 to the power of D, where D is the number of decades since the beginning of the year 1950. Number 1. Is the area of the forest increasing or decreasing with time? Explain how you know. To know whether it is increasing or decreasing, we are going to look at the factor. If the factor is greater than 1, it is increasing. If the factor is less than 1, it is decreasing. 5/4 is equivalent to 1.25. That means this is increasing. All right. So this is increasing because the factor is greater than 1. Number 2. What was the area of the forest in 1950? Well, this is measuring number of decades since the beginning of the year 1950. So this would be our original amount or our y-intercept, and we would find that right here, the number that is by itself. So in 1950, area equals 5,000 acres. Number 3. What was the area of the forest in 1940? To find that, 1940 is 1 decade earlier, so area equals 5,000 times 5/4 to the power of -1. 5/4 to the -1 is the reciprocal, because remember, negative means 1 over, and dividing by a fraction is the same as multiplying by the reciprocal. So this becomes 5,000 times 4 over 5. 5 goes into 5 once. 5 goes into 5,000 1,000 times. So 1,000 times 4 equals 4,000. So in 1940, area equals 4,000 acres. Was the area of the forest less than 1,000 acres in 1900? Explain how you know. So 1900 would be 50 years earlier, which is 5 decades earlier. So the area is going to equal 5,000 times 5/4 to the -5 power. So this becomes 5,000. Remember that the negative makes this the reciprocal. So now we have 4/5 to the power of 5. 5,000 times 4/5 to the 5th power. So 4 divided by 5 equals 0.8. And now we want to take that to the 5th power. And we get 0.32768. And when we multiply that by the original 5,000, we get 1,638.4. So that means the area was more than 1,000 acres, because we just calculated that the area was 1,638.4 acres. If you have any questions about how I solved this practice problem, please use this time right now to ask for clarification. A population of mosquitoes, P, is modeled by the equation P equals 1,000 times 2 to the power of W, where W is the number of weeks after the population was first measured. Number 1. Find and plot the mosquito population for W equals 0, 1, 2, 3, and 4. So first, if we look at the equation, 1,000 is the number by itself, so that is our y-intercept. We can put the first point when W equals 0 at 1,000. Next, we're going to look at the factor, and the factor is the number with the exponent. So now, each week, we are going to double. So if we start at 1,000, a week later, we are going to double to 2,000. A week later, we are going to double from 2,000 to 4,000. A week later, we are going to double from 4,000 to 8,000. And a week later, we are going to double from 8,000 to 16,000. So now we have our graph. Number 2. Where on the graph do you see the 1,000 from the equation for P? We see the 1,000 right here at the y-intercept. Number 3. Where on the graph can you see the 2 from the equation? The 2 is the increase. It is the factor. So we can see times 2 here. We can see times 2 in the growth from these 2 points. Then we see the times 2 growth again. And we see the times 2 growth again. So this is our growth factor. And exponential equations will always look like this. The number that is by itself will always be your y-intercept. The number that has the exponent will always be your growth factor. It's what you are multiplying by each time. If you have any questions about how I solved this practice problem, please use this time right now to ask for clarification. The number of copies of a book sold the year it was released was 600,000. Each year after that, the number of copies sold decreased by 1/2. Number 1. Complete the table showing the number of copies of the book sold each year. So 0 years since published would be the original amount, 600,000. One year later, that number would decrease by 1/2. So we're going to multiply by 1/2. 600,000 times 1/2 is now 300,000. A year later, 300,000 times 1/2 is 150,000. A year later, 150,000 times 3 would be, times 1/2 would be 75,000. And for some unknown number of years, we would simply take the original 600,000. We would multiply that by 1/2 times, or to the power of y, the number of years since it was published. Number 2, write an equation representing the number of copies C sold y years after the book was released. So all we need to do is take that final generic expression that we wrote and turn it into an equation. And using function notation, we would say C of y equals the original 600,000 times 1/2 to the power of y. Number 3, use your equation to find C when y equals 6. What does this mean in terms of the book? So for 3, we would say C of 6 equals 600,000 times 1/2 to the power of 6. 1/2 to the power of 6, we would think 2 to the power of 6 is 2, 4, 8, 16, 32, 64. So that would be 1 over 64. So that would be 600,000 divided by 64 equals 9,375. What does this mean in terms of the book? This means 6 years after the book was published, it still sold 9,375 copies that year. If you have any questions about how I solved this practice problem, please use this time now to ask for clarification. The graph shows a population of butterflies T weeks since their migration began. How many butterflies were in the population when they started the migration? Explain how you know. If we want the starting population, we are going to find that at the y-intercept. So we're going to see that right here when time is 0 and the population is 250,000. So the y-intercept is 250,000 butterflies. Number 2. How many butterflies were in the population after 1 week? What about after 2 weeks? So for number 2, after 1 week, there were, we can find that right here. 1 week equals 150,000 butterflies. What about after 2 weeks? We can find that at the next point, 2 weeks, 90,000 butterflies. Number 3, write an equation for the population Q after T weeks. So we would say Q of T equals the y-intercept 250,000 times the factor. So we need to figure out what the growth factor is. We can do that by choosing 2 points, taking the second y value, and dividing that by the first y value. 150,000 divided by 250,000 equals 3/5. And if we wanted to check this, we could even choose the next 2 points and say 90,000 divided by 150,000, and that also equals 3/5. So our factor is going to be 3/5 to the exponent of our input, which is t. Now we could use this equation to solve for the butterfly population after any number of weeks since migration began. If you have any questions about how I solved this practice problem, please use this time right now to ask for clarification. For an experiment, a scientist designs a can 20 centimeters in height that holds water. A tube is installed at the bottom of the can, allowing water to drain out. At the beginning of the experiment, the can is full. Every minute after the start of the experiment, 2/3 of the water is drained. Explain why the height of the water in the can is a function of time. So in this statement, we're saying time is the input and the height of the water is the output. As time goes on, water is draining out. This is true because at any given time, there can only be one height of the water. We could not say 2 minutes after it started draining, it was both 15 centimeters and 10 centimeters. So the height of the water is a function of time because for every measure of time there's only one measure of height. Number 2, the height h in centimeters is a function of f of time t in minutes since the beginning of the experiment. H equals f of t. Find an expression for f of t. Well, f of t would be the starting height, 20, times the factor. If 2/3 of the water is drained, that means 1/3 remains, and the power would be our input, t. So the expression for f of t would be 20 times 1/3 to the power of t. Number 3, find and record the values for f when t is 0, 1, 2, and 3. So f of 0 would be the initial starting height. So that equals 20 centimeters. F of 1 would be 1 second later, so 20 times 1/3. So that equals approximately 6.7. F of 2 would be 1 second later. We would multiply this amount times 1/3 again. And our amount would be down to approximately 2.2. And finally, f of 3, we would now multiply the 2.2 times 1/3. And our value is approximately 0.7. So, at 0 minutes, we are at the original 20 centimeters. After 1 minute, 1/3 of that is left, 6.7 centimeters. After another minute, 1/3 of that is left, or 2.2 centimeters. And after a third minute, 1/3 of that is left, which is approximately 0.7 centimeters. Number 4. Find f of 4. What does f of 4 represent? Well, we already know f of 3. To find f of 4, we would simply need to multiply by 1/3 again. So f of 4, we take this amount and we multiply it by 1/3 again. And our answer is approximately 0.2. That means after 4 minutes, the height of water is 0.2 centimeters. Number 5, sketch a graph of f by hand or use graphing technology. So we will use graphing technology. We start with 20 and we multiply that by 1/3 to the power of x. And our graph would look like this. So we can see that after 1 second, even though we start up here at 20, after 1 second, we're already down here at less than 7. By 2 seconds, we're just above 2. At 3 seconds, we're below 1. And at 4 seconds, we're below a half. So our overall graph looks like this. And number 6, what happens to the level of water in the can as time continues to elapse? How do you see this in the graph? If we look at the graph, you can see that as it continues, it gets closer and closer to 0 without ever actually hitting it. We see that where this flattens out. It will always get very, very close, but if you zoom in, you can see that there is always a gap, because if you're always losing 2/3, then you never actually lose that last remaining third. So the level of water flattens out closer and closer to 0. Mathematically, you would never actually empty the can. In reality, we know that we would actually empty the can eventually. If you have any questions about how I solved this practice problem, please use this time now to ask for further clarification. A scientist measures the height h of a tree each month, and m is the number of months since the scientist first measured the height of the tree. Number 1. Is the height a function of the month? Explain how you know. So for number 1, they want to know if the height is a function of the month. So remember, output comes before function of, and input comes after. So if we think about this, at any given month, can I have more than one height of the tree? No. If I go out and measure that tree, it can only be one height. So, yes, because for any given month, there can only be one height. Number 2, is the month a function of the height? Now, if we're thinking, if I measure the height, is that only going to give me 1 month? And that is probably no. The tree is going to grow, but at a certain point, it is probably going to stop growing. So if the tree grows to 20 feet tall and then stops growing, well, that height could be 20 feet after 20 months, and it would still be 20 feet after 30 months. So for number 2, no, because when the tree stops growing, the same height will give more than 1 month. So we need to remember that when we see the words function of, what comes before is the output, what comes after is the input, and for this to be a function, each input can only give one output. So number 1 is a function because any given month can only give one height, but 2 is not a function because the height can give lots of months once the tree stops growing. If you have any questions about how I solved this practice problem, please use this time now to ask for clarification. A bacteria population is 10,000. It triples each day. Number 1, explain why the bacteria population B is a function of the number of days D since it was measured to be 10,000. Again, is a function of. That means the population is the output and the number of days is the input. If it triples each day, then every day gives only one population. That means it is a function. Number 2, which variable is the independent variable in this situation? Independent variables are your inputs. So number of days is the independent variable. Number 3, write an equation relating B and D. So B of D equals the starting population, 10,000, times my growth factor, triples, means times 3, to the power of my input, which is D, number of days. If you have any questions about how I solved this practice problem, please use this time now to ask for further clarification. Number 1. Is the position P of the minute hand on a clock a function of the time T? A function of, that means position is my output, time is my input. So, if I have a specific time, how many positions of the minute hand can there be? Only one. So, yes, the position of the minute hand on a clock is a function of the time because for any given time, the position of the minute hand can only be in one place. Number 2, is the time a function of the position of the minute hand? That means time is the output and position of the minute hand is the input. In this case, the answer is no. If the minute hand is on the 3, then that's 15 minutes. But that could be 12:15, 2:15, 9:15. Just because the minute hand is in one place doesn't mean I can only have one time. If there are any questions about how I solved this practice problem, please use this time now to ask for further clarification. The area covered by a city is 20 The area covered by a city is 20 square miles. The area grows by a factor of 1.1 each year since it was 20 square miles. Number 1. Explain why the area A covered by the city in square miles is a function of t, the number of years since its area was 20 square miles. So, is a function of means the area is the output and the time, the number of years, is the input. If I have a growth factor of 1.1, that means the area is increasing. So, for any given number of years, there is only one area. Number 2, write an equation for A in terms of t. That means they want A of t that is going to equal the original area, 20 square miles, times the growth factor, 1.1, to the power of my input, t for time. If there are any questions about how I solved this practice problem, please use this time now to ask for clarification. The graph shows an exponential relationship between x and y. Number 1, write an equation representing this relationship. So if it is an exponential relationship, then y equals, our starting amount is the y-intercept. And we see that happens when y is 50. Then we're going to multiply by our factor. Now it might be obvious to some that our factor is 2, because we multiply 50 by 2 to get 100, and we multiply 100 by 2 to get 200. If it wasn't obvious to you, you can do just like before. Take the second y value, which is 100, and divide it by the first y value, which is 50. And you find that factor of 2. You could also use 200 divided by 100, and you would get that same factor of 2. So now we can put our factor as 2, and our exponent is the input x. Number 2. What is the value of y when x equals -1? Label this point on the graph. So as we're moving to the right, we are multiplying by 2. Well, to go in the opposite direction, we would do the opposite function. So instead of multiplying by 2, we would divide by 2. So now, when x is -1, we would have the point -1, and then 50 divided by 2 is 25. So the point is -1, 25. Number 3, what is the value of y when x equals -2? Label this point on the graph. So same thing applies. If we're multiplying by 2 when we go to the right, to go in the opposite direction, we're doing the opposite operation. So we're going to divide by 2. That means when x equals -2, y equals 25 divided by 2, which is 12.5. If you have any questions about any of the practice problems from today's worksheet, please use this time to ask for clarification before we move on to the next lessons.